Next, we discuss two very important differences between the linear and the nonlinear resistors. Let's take a current control type nonlinear resistor as an example. Now we have two currents, 2 amperes and 10 amperes respectively. Let's calculate the voltage U1. When I1 equals 2 amperes, U1 equals 50 times 2 plus 0.5 times 2 to the power of 3. It is equal to 104 volts. We can also calculate the voltage U2. U2 equals 50 times 10 plus 0.5 times 10 to the power of 3. It is equal to 1000 volts. They are easy to calculate, but it is very important to note that 1000 is not equal to 104 times 5. However, we know that 10 is equal to 2 times 5. This means that the homogeneity property of the linear resistive circuits we learned in previous lectures is no longer valid here. After the excitation changes into 5 times of its original value, the response is no longer 5 times of its original value. In essence, this means that the superposition theorem and the Thevenin theorem we learned previously are no longer valid here. Next, we take a look at the additivity. When I equals I1 plus I2, we use the formula to deduce it. U equals 50 times I1 plus I2 plus 0.5 times I1 plus I2 to the power of 3. We write it as I1 to the power of 3 plus I2 to the power of 3 plus 3 times I1 squared times I2 plus 3 times I1 times I2 squared. We put these together and write 50 times I1 plus 0.5 times I1 to the power of 3. Similarly, we can also write 50 times I2 plus 0.5 times I2 to the power of 3. We put the two together and write plus 1.5 times I1 times I2 times I1 plus I2. Clearly, this item is U1 and this item is U2. We also need to add 1.5 times I1 times I2 times I1 plus I2. It is not equal to U1 plus U2. Thus, the additivity is no longer true here. It suggests that the analysis of the nonlinear resistor circuits is certainly much more difficult than that of the linear resistor circuits. We have 4 important tools for the linear resistor circuits, that is the node method, the loop method, the superposition theorem, and the Thevenin theorem. We can find from this page that the superposition theorem and the Thevenin theorem are no longer valid in a general way. Okay, let's look at another difference between the linear resistors and the nonlinear resistors. Also, for such a current control type resistor, we assume that the excitation is a sine wave. We continue to deduce it. This time U equals 50 times 2 sine 60t plus 0.5 times 2 sine 60t to the power of 3. Expand it and multiply 0.5. It is equal to 4 times sine 60t to the power of 3. By using the triangle identical transformation, we know that 4 times sine 60t to the power of 3 is equal to 3 times sine 60t minus sine 180t. Integrated with the previous one, we know it equals 103 times sine 60t minus sine 180t. Did you find our excitation is a sine excitation with angular frequency omega being equal to 60 radians per second? But in the response, besides this omega, there is also a 3 omega. This means that in the nonlinear resistor circuits, there are new frequencies. This may be a good thing or a bad thing. It is good because we can produce all kinds of new frequencies by using the nonlinear resistors. In fact, In all kinds of communication circuits, these important features have been applied. Of course, it also has its drawbacks. That is to say, there might be a lot of frequencies that we don't want in the nonlinear resistor circuits. Next, we will show you through an experiment. Here we make a demonstration experiment of the nonlinear circuits. This is an experimental circuit board. The input is the audio signal coming from the computer. It's divided into two rows after the op-amp. One passes a linear resistor to the output, while the other passes a diode and op-amp circuit to the output. The circuit is controlled by a switch. The output is a speaker. When the switch is turned to the bottom, the audio signal passes through the linear circuit to the output. And when the switch is turned to the top, the audio signal passes through the nonlinear circuit to the output. We compare the difference between these two cases. Let's listen to it when the switch is turned to the bottom first. We heard the beautiful music. Now we turn the switch to the top. The beautiful music we heard before is changed significantly. The music is changed into the noise. This suggests that nonlinear circuits have the function of the frequency conversion. Okay, that's all for this lecture.